Welcome everybody to our 10th bioelectrodynamics webinar today with Professor Yuri Feldman. Let me give you some housekeeping announcements. So I would like to mention that also at the occasion of this webinar, we also celebrate IEEE Day. And this webinar is also supported by the International Union of Radio Science, URSI, and also by Engineering in Medicine and Biology chapter of the Czechoslovakia section of IEEE. Now to some more technical details. I would like to ask you so far to switch off your videos and keep muted during the talk. However, there will be space to ask your questions after the talk, and also you can write your questions during the talk in the chat. This time we have the lecture recorded, and it will also be published once we process it afterwards online on our YouTube channel, so you can view it. So we expect roughly 45 minutes of the talk, and then as much as we need for questions and answers. Now I would like to finally start introducing our today's speaker, which I really appreciate we have him here, because Yuri Feldman is indeed a guru of dielectric spectroscopy of the soft matter and biological materials. So Yuri Feldman, he received his master degree and PhD in Kazan State University, kind of combining radio physics and molecular physics, which is actually the combination I like a lot because I passed a similar track myself. Then from 1973 to 1991, he was with the Laboratory of Molecular Biophysics in Kazan Institute of Biology, Academy of Science of the USSR. However, in 1991, he moved to Hebrew University of Jerusalem in Israel, where he is currently a full professor and head of the soft condensed matter physics laboratory. As I mentioned, he's one of the primary researchers in this research field of dielectric spectroscopy of biomaterials. He was appreciated by several prizes, including the ones from Israeli government in 1992 and 2010 for his outstanding contribution to the development of Israel science. And also in 1998, he got a Kaye Award for best innovation and invention. Furthermore, Yuri Feldman is also a director of the Center for Electromagnetic Research and Characterization, and also he's a member of the boards of International Dielectric Society and International Society for Electromagnetic Aquametry. And as I think without further ado, I would like to ask Yuri to add anything he considers interesting or important, and then to start his talk. Yuri, the screen is yours.
Michael, thank you very, very much for your nice introduction. I'm really honored to be here, to be invited to this very distinguished webinar. And it's starting to be very popular now all over the world. And I think people are waiting now and learning from these webinars. Even I personally not so big fan of giving Zoom presentation because the feedback is not clear and it's very difficult to sit in front of the black screen and looking only on myself. Again, thank you very much, Michael, and I hope that in nearest future it will be possible to come and have the in-face meetings. So I'm stopping sharing my camera and sharing the screen, and I'll start my presentation. Okay, can you see my screen?
Yes, I can also see the part of the Teams. So if you can only highlight your PowerPoint.
Okay, so now you can see it now, right?
Yes, perfectly now.
Okay,
perfect.
great.
Thank you.
So Michael asked me to speak today about the protein interaction with water, and it's actually came to the station that we are really doing very close research, which actually answering of some of the questions, which also the groups of Michael is now working quite intensively. So microwave dielectric response of water in protein and protein conformation solutions. I especially put here this picture, quite old by the way, about the snow, quite unusual state of water in Jerusalem because usually it's not in condensed state. But it's a beautiful picture and quite rare coming, you see, in reality. The snow in Jerusalem, it's really an event. So I'll start today with an introduction to dielectric spectroscopy, because I'm not sure that all the listeners here are familiar with dielectric spectroscopy. Even now, this is starting to be a quite popular method. So dielectric spectroscopy, modern dielectric spectroscopy, is covering extremely wide frequency band from 10⁻⁵ Hertz up to 1012, and it's almost 18 orders of magnitude. Here, just showing you three actually main mechanisms which we are observing. This is, of course, deformation polarization when I'm applying electrical field, and I have the displacement of electrons and nucleus, and this is what you actually see as electronic polarization or atomic polarization when it's happening in the molecule. And this is actually refractive index and epsilon infinity in dielectric spectroscopy. We're also dealing with orientation polarization when you have this rotation of the dipole when you're applying electrical field. And finally, ionic polarization in very low frequencies when you have displacement of ions in the interfaces, and this could be extremely big polarization, but on a very low frequency band. Now, here I showed the limited frequency band, which is typical for biological systems, because it's not even interesting to go to 10⁻⁵ with biological materials, maybe only if somebody who is dealing with corals and very slow processes, but still the electrode polarization due to the very strong electrolytes will disturb you in this case. But here I showed you see the very fast mobility of water. If it's coming from the very high frequencies, this is from 100 gigahertz, and now even we extended to almost terahertz. Then we see the tumbling of the amino acids or anisotropic mobility of polar or charged groups of lipids in the membrane. Then tumbling of the proteins as a whole, and this is around meg or hundreds of kilohertz. Then very important interfacial polarization of cells. Finally, we are coming to the very low frequencies and slow mobility of ions on the surface of DNA, RNA, and this is already around kilohertz and even hundreds of hertz. Of course, the same frequency band is relaxation of ice, and finally tissues, and the slow mobility of ions on the surface of the interfaces in the different tissue structures. Okay, now many years ago, Hermann Schwann, who measured the first, I think, the tissues in a very wide frequency band, he defined the three main processes which he observed in the frequencies up to microwave. So it was alpha process, which is usually you see this mobility of ions on the interfaces in the tissues. Then beta dispersion, which is usually interfacial polarization of the membrane of cells. And of course, there could be also from nuclei and not only from the cell envelope. And finally, gamma dispersion, which he was defined as the process which is coming from the water. Now, water in this case, and this is already the paper of Grant, and I took this cartoon from the Grant paper, where this is the tumbling of the protein. This is myoglobin, quite high concentration, 16% of myoglobin in aqueous solution. Gamma process, again, water, and then delta dispersion, which I think till now there is a big arguments about what is this. Quite a lot of people starting from ground, they're telling, okay, we see here the bound water. This is the hydration water. This is the water which is really surrounding the protein. And we can see this delta with some kind of energy activation and also some kind of like the body relaxation and so on. And these speculations are coming even up to now. I think the last paper of Luckenheimer was published in 2012, and there was another paper of committee 2014 where they are saying we are studying the bound of hydrated water in aqueous solutions. However, it's still a question of debate because there are a few papers who show that it's actually not the relaxation of bound water, but relaxation of the amino acid residues mobility, and they showed it with a nuclear, with neutron scattering and nuclear magnetic resonance, that it's really not bound water. Now let's see what's going actually on with this delta dispersion, and can we really study this bound water in this case? Water actually can be considered as a marker of dielectric measurements because it's like you see the contrast material in the computer tomography, because it has large dipole moment. And of course, if you know that water in microwave in the liquid state, and this is relaxing in the microwave with a quite narrow temperature interval 0-100 degrees, situated around 100 gig up to few gig. And this is the very narrow range of temperatures where you can see the microwave absorption of water. But if you are coming to another condensed state, you have a jump of 7-8 orders of magnitude. You see ice is here, 10-4. Water is here, 10-10. And this is the reason why you really can make a very nice experiment to heat water in the ice cap. Actually, if you take a big piece of ice, make a small hole, put water and put it in the microwave oven, which is 2.5 gig, and there is the power is something well few megawatt, you can in 20 seconds heat the water in the ice cap. Of course, it will keep longer. The thermodynamics is working, so the ice will melt. Now, water is shifting when it's starting to be ice. But what is shifting when it's also hydrated? What is shifting when it's confined? And all these things means that when you are hydrated water, when water came to the bound state, is disappeared from the microwave. So it's very interesting also to see that the temperature dependence of delta epsilon of ice and water have the same range, have the same law, the Curie-like behavior. And the relaxation time, when you're speaking about the reciprocal temperatures, this is 0 degrees, behaves with Arrhenius law up to melting or freezing point, with energy 0.2 electron volt, 20 kilojoule per mole, and then we have a jump. And then quite interesting, quite non-Arrhenius crossover, and then very interesting behavior here. Now, briefly, we have to discuss the dielectric relaxation mechanism in water. It's going to according to the weight and switch model for defect migration, which was introduced by Katz in 2001. And some dielectric properties of ice and water are really almost the same. Both systems demonstrate the bi-type relaxation near the melting point. It's interesting that when you're measuring bulk water, it's really the bi. One relaxation process, no any kind of broadening, and this is really described by the Dubai formula. Then the temperature dependence of static permittivity is going according to the Curie law. Now, what types of the defects we can consider in this case? Jerome introduced defects in 1953, and he called this L and D defects, and there are two types of defects: orientation, when you have two oxygens close, and this is L defect, or two protons are close to each other, and this is D defect. And then due to the electrostatic repulsion, you see we have a really very fast reorientation of these molecules in the vicinity of these defects. Now, another types of defects are ionic defects, and OH or OH3+. So we have here 3 protons, and this is going to move on this network of water or ice structure as a diffusion of the protons or proton hopping. So rotation dynamic is coupled with the diffusion of defects. You see here I show how the defect is moving through the network of water molecules. So we can reduce the problem of water molecules rotation to the problem of random walk of defects. This is what actually we did only 5 years ago, yes, 5 years ago. So where we described the complex permittivity of water through the number of the charge of the defect, positive charge defect, D defect, hydronium, or bifurcated oxygen. Then negative charge defect, L defect, or hydroxide, or bifurcated proton. So N is the number of defects, and R square omega is mean square displacement of the defect. So all these ideas are really actually confirmed by other methods, because tau on T divided on eta is a constant. D tau is also a constant. T1 spin lattice relaxation on tau is a constant, and no reaction on pH time relaxation correlate with viscosity. If you add pH or change pH in ice, you see that there is a dependence. In the case of water, is just orientation defects are dominated in this case. Now, what's also interesting, that when we describe with our model all the band up to infrared, we can see that R is the maximum of the mean square displacement. This R square is 6 delta epsilon, the amplitude, and this is diffusion defect on tau defect. And we have this, in this case, the recombination with creating normal H bond. So actually annihilation of these defects, defect and anti-defect. And we are coming to this very interesting radius of every cluster of water, because radius R can be attributed to characteristic scale of dielectric relaxation or to the size of the water cluster. Time relaxation is the mean lifetime of the defect. This is our model, which we published in 2016. Now it's have a quite big number of references. And we started to use these ideas in order to understand also what's happening with water when it's already not just bulk, but it's a solid. Now, is water in the glass and biological cell are the same? This is the question which people started to ask, we see, in 60s of the last century. And they told that water here in the glass and water in the cell, you can see the difference. This is very, very, very concentrated solution of any kind of proteins, amino acids, ions, whatever. And they told this is the same. Why they told this? Why it was quite a paradigm for almost 40 years that water in the glass and water in the cell, water in the leaves, water in the tissues are the same. Because NMR, diffusion coefficient, and the electric relaxation time for these two measurements are almost the same. So what's the difference? Because when you are putting something in water, or when you're putting water somewhere, instead of Dubai, as I told you, the Dubai is from 0 to very high temperatures in bulk water, and also near the melting point, also Dubai, and also for the ice, up to minus 37 degrees Celsius, also Dubai. So it's a very nice single relaxation Gaussian, and with a quite critical value of relaxation time. But if you're putting something in water, you immediately have the broadening. And this broadening actually depends on what type of the molecules you're putting inside the water, what type of the solution you're getting. Or it will be electrolyte solution, like this, or it will be the dipole solution, like here, the solution of glucose. So another parameter which also was never considered before is the amplitude of this relaxation process and the B function which was proposed by Fröhlich, which he proposed it for the solid state, but we try to apply this for the liquid. And it's interesting, when the system is really liquid-like, this function is decreased with the temperature. If this is solid-like, it's increased with the temperature. And if the system is uncorrelated, then it simply have no any temperature dependence. What does it mean correlated? Here, m square, here we have cosinus theta. Here is the cosinus between the two dipoles or the two units with a specific orientation in any kind of the condensed matter. Now, Kolkol, and quite some time ago, see, it was already 2002, so almost 20 years ago, my former postdoc, Dr. Ryabov, proposed that alpha, this parameter of the broadening, is actually have a physical meaning, and this is the rate of interaction, n is the number of interaction of the dipole with any kind of matrix. And this is the dimensional time when we really have this macroscopic relaxation time which we are measuring, and tau naught is the cutoff relaxation time. So he built some kind of theory which was very successfully applied for polymer solutions, but for some systems it doesn't work. So we actually in 2010 rebuilt this model, and with a very simple transformation we got this, that n tau, the average number of relaxation arcs during the interval of tau, is the tau and tau naught in power alpha, where alpha is the fractal dimension of relaxation arcs in time. And then we got, with such kind of simple changing variables, we got a very simple hyperbolic dependencies for tau more than tau naught and for tau less than tau naught. And then, depending on the what kind of the phenomena we're observing, we have a first or second or the third or fourth quadrant. Now, when we started to apply this to different solutions, we saw another very interesting feature. When I'm working with the solution of the dipoles, like sugars, like amino acids, non-ionic amino acids, like proteins, I have usually redshift. And we understand that it's when we have dipole-dipole interaction. Dipole of water interact with a big matrix, which is a big dipole. So dipole order H-bond network, amount of defects are decreased, and we have delay of the main relaxation time. But if I'm working with ions, I always have a blue shift. My ions are making you see the disorder of the H-bond network, and amount of defects is increased. So this is the real experimental data. This is water. This is glucose. Big concentration, 1 mole, 2 mole, and you see very significant red shift in this case, you can see. And here, the blue shift, sodium chloride, also quite high concentration of ions. Now, using these three parameters, alpha, logarithm tau, and logarithm b, I can build a new type of trajectories, or new type of the phase diagrams, where alpha, logarithm b, and logarithm tau give me opportunity to see what type of interaction and what type of dynamics and structure I observe in such kind of solution for the dipoles of water. Now you can pay attention, glucose, dipole-dipole have the first quadrant, alpha logarithm tau, but ionic solution have the second quadrant. Now, knowing this and monitoring red blood cells, for example, also only for water, we found that there are quite interesting changing of this alpha logarithm b and logarithm tau parameters for the cells who are coming from the young state to the old state. These are the cells which can bring us oxygen, and this is already the almost dead cells. They cannot transfer the oxygen with hemoglobin through our blood. Now, when we started to analyze these parameters, we see that relaxation time changed only during this transition period of time from the native red blood cells, erythrocytes, to the already not active red blood cells. Delta epsilon almost stable up to this period of time of 21, 30 days, depending on the donor. And also we see then starting to decrease. But alpha, starting from the second week, from the 14th day, we can see there is a linear dependence. It's like a clocking. We have a timer in red blood cells which are showing us when actually happening something with the cell. And then when it's already died, you can see it. It's stable and not changing. It was really amazing for us. We published this paper in 2017, asked ourselves the question, what is the reason why we are measuring only water in cytoplasm can see this state of the cell? Don't forget, we are measuring only water. We are measuring only in microwave. And it was really for us quite unusual and unexpected that in 2016 we found a paper where people measured the T1, the spin lattice relaxation also of the cytoplasm in red blood cells, and they saw very similar behavior. This is the black line. This is actually average line for something like $17. Here we have only 2 donors for dielectric spectroscopy. Now, spin lattice interaction of protons of water in the case of NMR, and dipole matrix interaction of water interacting with the protein in dielectric spectroscopy, giving us very similar prediction when something happened with the cell. What is the reason? So we ask ourselves what is the reason. We started to work with hemoglobin because hemoglobin is actually the biggest concentration of proteins in red blood cells. I was really surprised when I learned that there are 300 million hemoglobin macromolecules in one red blood cell. Can you imagine this concentration? Now, we measured this with a new PNA, which allowed us to measure from 10 meg up to 50 gig. We use this high performance probe and special temperature jet in order to control the temperature. And these are the spectrum. This is the bulk water. This is actually the aqueous solution of methemoglobin, 330 gram on deciliter, 30%. This is actually almost the physiological concentration of hemoglobin in red blood cells. And you can see that when I'm changing the concentration, it's very nicely reflecting the amount of the water in such kind of the hemoglobin solution due to the decreasing dielectric permittivity. The static dielectric permittivity is proportional to the amount of water which we can see in this frequency band. And you see also the broadening of the peak. So we compare also deoxy and oxyhemoglobin. Now, deoxy and oxy, they have some conformational change. And this is here the pocket where we have more water and here less water. And we want to compare what's going on with the oxy and deoxy when putting this in PBS solution. Now, what we saw. So this is relaxation time after we feed our spectrum with cold, subtracting the conductivity. And we saw that it's a very interesting behavior of relaxation time with the increasing of concentration of hemoglobin in PBS solution. First, we have a decrease up to 10 gram on deciliter, and then increase. Now, decrease, which is showing me the blue shift, clear because of the quite high concentration of sodium chloride and other ions in PBS. And here the protein is not contributing too much in terms of interaction water with the matrix. It's mostly dominating interaction of water with ions. But when the concentration increased, we see already quite significant change in this case. Moreover, as you can see, the oxy have much slower decay than deoxy. If you're looking on the delta epsilon, there is almost no difference, and we really cannot distinguish in the case of the hydration between the two different states of the protein. But alpha showing us quite different, significant difference in this case. You can see it. Now, if I'll put the trajectory, alpha logarithm tau, I can see this is the first quadrant. And in the first quadrant, I can define this, the minimum relaxation time cutoff, TC. And in the small concentrations of a protein, I have this second quadrant where the most interaction is coming from water-ion interactions. Now, what's interesting that in the case of the oxy, I have much bigger cluster in this case than in the case of deoxy. Why? Because the number of the apolar surface area A square in the oxy is much bigger than in deoxy. And polar is smaller in oxy than in deoxy. So it's also explaining you why the viscosity in the oxyhemoglobin is much bigger than in the oxyhemoglobin. And this is our colleagues from the Institute of Molecular Biology of Engelgard from Moscow make this simulation. You can see quite condensed deoxy state and more more flexible and bigger scale of the oxy of hemoglobin. You can see it. Now, another question, how much water is bounded by hemoglobin? And here again, quite interesting situation, because if you look on the distribution function, radial distribution function showing the solvent layering near the protein, and this is simulation from the paper from 2008, you can see here first salvation cell, second salvation cell, third salvation cell, and the traces of the fourth salvation cell. Something like 6 angstrom from the surface of the protein. Now we use in this case the B function from Fröhlich, which is actually proportional to delta epsilon. And then actually we see from another side, this is the macroscopic dipole moment, the correlation function, which is actually related to the average cosinus or Kirkwood factor. Now you can see how this function normalized on the B0, which is the B function of the pure solvent. You can see that this is in double distillate water, and this is in the PBS. If here we see the conformation change all the time, here we have only 2 slopes, and this is 10 gram on deciliter. Exactly here we have the only concentrated solution of protein dominating interaction between the dipole of the proteins, and here the dominating of interaction with the ionic ions in the buffer solution. Now, evaluation of the structure of methemoglobin in double distillate water is quite simple. This we have this M double distillate, which is my dipole moment of hemoglobin, and this is the water molecules. And this we made all this averaging and succeed to calculate the number of water molecules of hydrated water molecules in this hemoglobin solution. In the case of PBS, it's much more complicated because we have to take into account the negative and positive charges, and the interaction between the shells around PBS ions with the same sign is negligible. We're considering this, and the excess of positive charges in PBS compensate the excess of negative charges in the surface of methemoglobin. It means that all my groups of the amino acids on the surface, where I have negative and positive, I'm creating some kind of dipoles in this case when they are canceling each other, and I'm not taking into account this ionic interaction. Now, as I told you, 300 million of hemoglobin macromolecules, very dense packaging of the hemoglobin molecules inside the red blood cell. This is like this. You see, it's really extremely concentrated. In the beginning, when we started to measure such kind of concentration, I was sure that we almost see the hydration water. There is no bulk. But what was found that N free to N bound, according to our calculations, stabilized on a very high concentration and coming to the 4 free molecules to 1 bound molecule. So actually here I have a very nice agreement with the experiment and theoretical calculation, which is showing that about 3 grams on deciliter, each hemoglobin molecule is covered with a layer of 5 angstrom. So between 2 molecules, I have 10 angstrom of water. And when we made such kind of calculations, we understand that in the bulk water, in the aqueous solution of the protein, I have almost 80% of water in the free state and only 20% of water in the bound state. It's unbelievable from one side. From another side, it's very clear that red blood cell have a lot of bulk water in order to allow diffusion of gases inside the cell, and this is actually the reason why if you quench red blood cell, you can break the membrane, because they're creating the ice and increasing the volume on 10%, which is breaking the membrane. So what actually we show here, that it was possible with microwave direct spectroscopy to measure the difference in interplay between the hydration and bulk water for hemoglobin recombination for oxy and deoxy states. Using microwave direct spectroscopy, the dielectric properties of cytosolic water became a powerful tool for assessing the impact of stress, diseases, or drug on red blood cell properties. This approach will not distinguish between the impact of hemoglobin oxygenation and changes in other cytosolic components such as ions, metabolites, or other molecules, but it will reveal changes in the bulk water state in the cells in response to treatment. The use of parameters such as the broadening parameter alpha, relaxation time tau, and electric strength delta epsilon as prognostic and diagnostic markers requires further validation. And this is true. We're still working on this. We're still trying to understand what actually we can learn from trajectories when we have some kind of kinetics, we have some external parameters which are changing this alpha, tau, delta epsilon trajectories. And in concentrated hemoglobin solutions, for each hemoglobin bounded water molecule, there are 4 molecules of free water. This was really quite unusual result for us and very significant, I think, for biological systems. And finally, I want to acknowledge and appreciate the contribution of Dr. Larissa Latypova, Professor Alex Kuzenko, Dr. Ivan Popov, with whom we created the water molecule, with the model of water, the relaxation of water, Dr. Paul Banishai, with whom we started with Alexander Kuzenko all these games with trajectory, Dr. Gershon Barstein, our biological guru, and Leonid Lifshitz, without whom we cannot work with these cells and macromolecules. Professor Anna Bogdanova, guru in red blood cells, she really is guiding us, and the team from Moscow Institute of the Institute of this is Institute of Engelgard. I forgot the name of this institute, but it's biochemical. This is Institute of Bioorganic Chemistry. So, and Irina Petrushenko, Anastasia Nashkina, and Yuri Feldman, who really helped us to make this simulation, and Dr. Angrin Bao for the extremely helpful contribution to this work. We are grateful to Keysight and Intelligent Ref Microwave Solutions, who help us with all our systems to maintain them and to hold them in the proper way. And the Swiss National Science Foundation and Israel Science Foundation grants for supporting this work. Thank you very much for your attention.
Thank you very much for a very interesting talk. So now this floor is open to questions. I think I'll take an opportunity to, oh, there is rising hand. So let's go opportunity first to attendees. I have a couple of questions back up. So I see Ogan Gurel is raising the hand. So Ogan, I will allow your mic and camera. So mic and the camera, so you can ask your question yourself, Olgan.
Okay.
Hello, Yuri.
Yes. Hello.
You hear me? Hello, Yuri.
Hello.
Absolutely fabulous talk. Nice
I
to hear.
simply try to stop sharing the screen. I'm stop sharing the screen or not?
Yes.
You stopped, but we cannot see you, Yuri.
I'm trying to see to switch my camera, but not yet. Oh, okay. I think now it will be okay. Now it's okay. Hi, Olgan.
Hi, Yuri.
Yes.
Great to see you. I'm here in Montreal, and you're in the Jerusalem, and Michelle is in Prague. It's amazing. First of all, not as amazing as your results, though. I was very happy to hear about the distinction between bound and free water, and your studies on hemoglobin. Absolutely fascinating. I'm glad I joined. Thank you. I have a question very quickly. What's very interesting about the physiology of red blood cells is that when they go through the capillaries, they get very squeezed. In fact, that's one reason why they experience this aging, as you noted, over the 90-year cycle. And I was fascinated to know about this amount of free water, which you very nicely explained in terms of the diffusion. You also explained, if I interpret correctly, that the oxyform, which is in the arteries, is sort of more open and has some extra water around it. And then the deoxyform, which is now being squeezed in the capillary, has less water. Did I interpret correctly?
Yeah, I think yes, and of course this biconcave shape of erythrocytes, which really then go for deformability in the capillaries.
Yes. So
it's of course changing the pressure inside and outside the cell.
Exactly.
And of course, there is a compensation from the membrane and also the ions involved. But don't forget, we are measuring only water. We are not measuring the membrane relaxation, membrane interfacial polarization. We are sensitive only to water. We are measuring the average cell because we're using the mixture formula and recalculating what is going on in the cytoplasm. What I showed you for red blood cells, it was for one average cell. And this is interesting that the parameters of call of the cytoplasm versus aging, time of aging in the store is changing continuously for the broadening of the spectra. The broadening continuously starting to change from the 14th day of storage. But then suddenly on the 21st or 28th, depending on the donor, it stopped, it jumped, and that's all. So actually we saw clocking. We wanted to understand what is the reason of this, why it's coming. All this is due to the hemoglobin, all this is due to the membrane, all this is due to the actually the cytoplasm, the ionic solution inside the cytoplasm, which is going out to the buffer. This is what we're still asking ourselves, and this is still have to be studied in more details.
Yes, so that relates twofold to my question. One is whether it's the membrane, because the current sort of biological thought is that the membrane degrades in these senescent or older red blood cells. But my other question is, could the pressures in the capillary being squeezed literally change these dynamics? And in other words, forcing in a way the deoxy form of hemoglobin as it's being squeezed, because in effect less room for water is there. I mean, I've never thought of this, but your results seem to point, in other words, there's a biological, physical mechanism for mediating these conformational changes, not just a chemical mechanism, but a physical, biological one. What are your thoughts on that?
I would like to make these joint experiments with Katia Gainarov, who made this microfluidic system with a
microfluidic.
Microwave actually strip line, and to measure the spectrum for one particular cell when we're putting this in the channel and starting to make a squeeze. I'll be very happy to work with her, especially on this experiment. It will be great.
I think that would be amazing, because you see this physical phenomena spectroscopically being detected, if you will.
Yeah, you are right, but I unfortunately have no such kind of expertise like Katia making with a single cell chip, so it's a cell on chip. And
Yes.
we're working up to 75 gigs. She can do this with only one cell. I think we have to combine our efforts together, and maybe we can succeed to do something.
Yes. Well, I'll definitely be following. Once again, thank you very much.
Thank you, Alan. There another question, yeah?
Yes, another question from Vladimir Beres. Let make him allow the microphone and camera. Vladimir Beres, you can ask a question yourself or like to type into the chat, whatever you prefer.
Okay, may I ask the question? Thank you very much for interesting talk. Here is the greetings from Kharkiv University in Ukraine. So first of all, can I add some notes to the previous discussion with the previous speaker? As for the decrease in the bulk water state and the dielectric properties of red blood cells stored for longer than 20 days, it is possibly the decrease caused by microvesiculation, where parts of plasma membrane invaginate inside of the cell, making so-called membrane body. And due to formation of those small cavities inside the cells, filled with also water and lipids and other proteins, you can see that dramatic change in the electric properties of all that. This is just an idea on why this could be so, because this such microvesiculation is well-known phenomenon in observed in the time course of the red blood cell storage.
I will agree with you if I'll see also delta epsilon decrease after 14 days, which is not the case. Because then you are right, the amount of bulk water which is actually participate in this frequency is really contribute, and then it's disappeared due to such kind of the micro, it's nano bubbles, say nano bubbles.
Yeah.
But we saw that delta epsilon stable, tau is stable, and only alpha starting to be sensitive. So it's changed the type of interaction due to the aging. So we saw the timer actually in the broadening or the rate of interaction. So the rate of interaction is actually increased during this time, starting only from the 14th day. Before it was everything stable. And the same happening with the T1. As you saw from this Austrian group, the T1, the spin lattice relaxation time is also stable up to the 14th day. And only then the protons starting, you see, to change this rate of the relaxation. Strange. I have no answer. Maybe you are right, but we have to verify this.
I see. And my question is whether it's possible with the help of your technique to distinguish between, say, extracellular water and the water in the cytoplasm. Or you are performing your experiments, we have, say, only red blood cells with very limited amount of external water.
No, but here it's very simple. We are measuring, you see, first suspension. We have the electric properties of the suspension. We measured separately the electric properties of the buffer. Then using the mixture formula, in our case, we're using Krashevsky, but you can use any other mixture formula. We're just subtracting the properties because membrane is not contributing, the protein is not contributing, lipids are not contributing on these frequencies, so only water. So we're actually using this mixture formula, we're taking and getting only cytoplasm, but it's average for all the cell, of course. Now, it depends what type of buffer you are using in this case. And Dr. Larissa Latipova and Gershon Bernstein, they just made some measurements on controlling the buffer when it's going through the aging. And they saw that it was not correct, which we used before, to use only the clean buffer. We have every time to take the buffer which was exactly this period of time. And this is also the trick. So the buffer also changed, but it's a question, what is going out from the cell? What is changing the properties of the buffer?
Okay, thanks. Thanks again for interesting talk.
Thank you.
Thank you for a very interesting question, and also interesting comment that Yuri made on these, that the cells are changing the buffer. I mean, it's something obvious, but it's not obvious when you're measuring dielectric properties. So it's very important to check that exactly as you mentioned.
Not obvious at all, and I think that I don't remember we published this paper or not. If I think that it was already published, so I can send this paper on the buffer study if it's already published. I don't think
That's very interesting. I definitely will be curious to see that. I see another raised hand from Minopar Babak. So let's make him let his microphone allowed and also his camera. So you can ask the question yourself. Babak, if you are.
It's very, very interesting talk. I learned quite a lot. For me, it was a question to understand when, for example, you are doing the hemoglobin study, when you have in the cell and all those complications that the people they were asking those questions also, to just compare it in hemoglobin in water to see that maybe this is related to the folding on or unfolding depending on the concentration is happening and to what is going with the dynamics of the water.
No, but here I think maybe I don't understand your question correctly. So the main point, how water contribute to the conformation of the protein, correct?
My point is that, of course, you know, when you are changing the concentration of, you can change the concentration of your hemoglobin in the solution, just hemoglobin in the solution, not in the cell, and compare it with all those data you have got it from the cell stuff to see it maybe there is something related to the concentration effect of the water with the hemoglobin, which can be in some concentration it is going to be folding of unfolding, which is influencing the structure and mainly getting the water influenced by that.
I got it. Now look, you see, we try to keep the protein in the native shape, and this is the reason why we're using the proper pH and the ionic strength of the buffer. So the protein in the proper conformation state, which is actually able to get the oxygen or to return back to the oxygen. Now we saw that we are measuring only water. We didn't look for the tumbling of the protein or any kind of mobility of these units of the protein because it's on much lower frequencies. We can actually see the traces of this. If we go up to 10 meg, you can see this mobility, but we took it out. We didn't consider them. So here we look only on water, and we saw that for different two conformation state, oxygenized and deoxygenized, we see a huge difference in the mobility of water and its interaction with the ion, the charge or amino acid residues on the surface. And even more, it's decreased the viscosity significantly for deoxygenized. It increased viscosity for oxygenized. Why? Because of change of the surface on interaction rate. So actually, water in this case, the consequence of this changing of the viscosity due to the conformation state. You understand? So it's
yes. Thank you very much. And if I just commented that this can MD simulation can a little bit help to see that, you know, this information concerning to surface accessible area for the protein can be checked, and then how much depend on the structure you have, different structure you have, how much the amount of the surface can be accessible for the solvent.
Exactly, you're absolutely right. But everything is published. If you want, just send me the request and I'll send you the papers.
Thank you very much.
Okay.
So thank you. Very good question, actually, to relate now to my question I had. So I was wondering, Yuri, if you demonstrated these like examples, like when the red shifts and blue shifts are taking place, considering dipole-dipole or dipole-ionic interactions, right? And there, I'm curious. So is it like consistently the case that whenever or if you have a like also data for that experimentally, if there is a blue shift observed for let's say these, you adding just NaCl, just simple salt, that does it also correspond that macroscopically, the dynamic viscosity, if it's measured, by independent methods, as by viscometer, does also decreases? I'm addressing the standard relationship of relaxation time to dynamic viscosity.
Yeah, you're absolutely right, because you see viscosity, of course, in the sodium and potassium, especially, that see, for example, when you are coming to the quite unusual conditions, 1.8 molar.
Mm-hmm.
So it's like viscous liquid on your skin, and of course viscosity, macroscopic viscosity, if you will measure it with a standard viscosimeter, will be definitely higher.
Okay.
But
okay.
because here we are looking only on water, and we are using in this case the Debye formula of water, we are making estimation what type of viscosity of water in this case will be if the size of the water molecule is still the same. So I see the effective viscosity change or microviscosity of water, which is actually increased in this case. In the case of ionic liquid, probably it will be decreased.
Okay, interesting. So you think that it's still like if you, okay, because effectively what you said, the effective size of the water molecule might be changing too,
The
right?
cluster. No,
Cluster. Okay.
Again, we use very primitive idea that in the high concentration of hemoglobin, we saw the Debye like behavior. Relaxation time is really following viscosity in this case, and I implied this actually not correct idea that this is just tumbling of water molecule. This is just first approximation. You're right, we have to measure with a very precise viscosity or microviscosity with EPR. Then you will be more correct.
I see. Yeah, because we, in our recent papers, we also used very naive approaches how to interpret the shifts of the frequency of the imaginary part of the permittivity peak. So basically, it's related to relaxation time of water, and we mostly argued only with the viscosities. But in our experiment, we just luckily had a cases that also macroscopic viscosity increased, and then we could see that there indeed the water peak shifts to the lower frequencies, which was consistent. But the fact is that the macroscopic viscosity as measured by viscometer might not be the same effective viscosity which is governing the relation.
Absolutely right. Absolutely right. Because here we have to consider two things: macro system and micro viscosity in the vicinity.
Okay, I see. Yeah, this informs a lot our potential decisions to buy the viscometer or not.
Yeah. I would like to buy the viscosimeter, but if you want to buy, it's not simply the viscosimeter. Of course,
it has to be the cheap viscometer.
Measuring, you see the time of through the capillary. You really have to buy a very nice system. It's costly. It's 20,000.
Yeah.
20,000 euro if you want really to have very precise and a very broad range viscosimeter.
Yeah, it's something we considered. Cheap. Yeah, I'm not going to make any advertisement, but there are very nice chip-based micro viscosimeter, which is like commercially available, and that could do the job, measuring few tens of microliters. But they would be interesting.
Send me please the link.
Okay.
Without any kind of marketing, I just simply would like to see that.
Okay, good. Are there any more questions in the audience? I don't see any more raised hands so far. Okay, so anyway, I mean, I think that model and applied again, which you developed over recent years, it really makes me more and more convinced we should start to have a look on it and apply it too, because it will give better interpretation of the dielectric data we are getting, at least in the microwave band. So that's maybe my kind of almost final comment from me. So I also encourage other people to look on that, because so far what I see, it's conceptually the most complete, probably, I mean, for me at least, as I understand the model of the water-based dielectrics. So it's very interesting to have a look on those.
Okay, thank you very much again for attention, and Mikhail, for your invitation. I was really pleased. Even the Zoom presentation is awful. I can tell to everybody. When I don't see anyone, it's so difficult to speak. Okay.
Yeah,
Thank you very much.
Very well. I think it was very informative. Thank you very much, and we will keep in touch. And hope to see many of you in the next webinars. So have a good day.
Thank you. Bye bye.
Bye.